All right, so today we'll also be online, obviously. And then I think on the May 30th, I'll be there for the whole day and giving the lecture live. Okay, let me turn on Zoom. Here we go. Okay, so just ultra quick reminder of what we discussed last time. So we discussed asymptotic series. They appear basically everywhere: quantum mechanics, field theory, string theory, whatever. Some examples: zero radius of convergence. There's the factorial growth. There's the subleading exponential growth that already has some hints on the physics of the non-perturbative sectors. It sort of can predict large order, decode large order. Resurgence is sort of relating everyone to everyone else. Trans series puts everybody together. And there's these infamous numbers, Stokes data, which are hard to find. They, of course, relate to Stokes phenomenon. And then eventually we started looking at, well, some nomenclature about Borel transforms, about Borel resummation, the fact that there are singularities at some places on the Borel plane lead to Borel resummations that are nonetheless relate to each other via the Stokes automorphism. The Stokes automorphism being the exponential of a derivation. We'll talk more about that, I think, next time. Discussed a bit about trans series. And then we started looking at this example, which was a linear example of a quote-unquote partition function in one dimension of a quartic potential. We discussed saddle point analysis, steepest descent contours. And then to try to get all non-perturbative content, we wrote down a differential equation, sort of a Schwinger-Dyson, if you want, equation for that super simple partition function. This is actually just a Bessel function, a Bessel equation. And then we start analyzing it, studying the trans series. The trans series effectively is just, in this linear problem, is an elementary statement about differential equations, and just the space of solutions is two-dimensional, and the trans series parameters are just boundary conditions, or the initial conditions. We could write down Borel transforms exactly, and then we looked at the expansion of the Borel transforms, that they naturally have log branch cuts, and at the log branch cut we see the resurgence of the other sector. So here was the perturbative sector, and we were seeing the resurgence of the one instanton, quote unquote, non-perturbative sector next to the log branch cut. The same happened for phi1. And then we discussed how to write all this down in a very simple way using these alien derivations with a definition which is immaterial because it only applies in that specific example. What we're going to discuss today, the definition is much harder. I'm not even going to give it, but it's just illustrative. And so the trans series for that example is just a perturbative sector, a non-perturbative sector, and the alien derivations allow us to sort of move in between these two sectors. And so they sort of allow us to see at the singularities the resurgence of the other sectors. We discussed a bit of Stokes data and Stokes phenomenon, how that actually works very nicely. And we ended up discussing the Cauchy theorem. We'll apply it today again, and wrote down a large order expression. And just to recall you what that looks like, because I will be showing more of those today. Where's the mathematics screen? Here we go. Let's see, where were we? Yeah, we saw all these in mathematics. Let's not review what we saw in mathematics. Just remember that that's how we ended last time, making basically generating coefficients of that Bessel function, and then using, I will tell you a little bit more about Richardson transforms later today. It's just a numerical thing, so it's not even something we are going to dwell on a lot. We could sort of see what large order predicts. So this red thing being just what comes out straight of, let's call it bare large order. And upon some numerical improvement, we could predict, I think this was the first, what was it? Yes, this is the prediction for the Stokes coefficient, which is square root of 2 or something like that. Okay, so having said that, let's go on with today's lecture, where we just basically reviewed that example once again, but now sort of quote unquote non-perturbative. So the idea is, of course, elementary, because we're gonna keep going with this example. So it's slightly harder, but still quite simple, because at the end of the day, what we are going to be looking at, it's basically if last time we looked at the partition function, which was just a one-dimensional quartic integral, today we're going to look at the free energy, which is basically just a log of Z. Okay, so you could say, well, there's nothing to do. We already computed Z. Yeah, well, that's true. But again, it's not like I want to compute, the Bessel functions again. This is 200-300 years in the past. I'm just giving simple examples to try to see how all the machinery works. And then in the next 2 lectures, of course, we will depart from simple examples and look at harder examples without, going through the gory details, actual calculation, just reminding you what we saw in simple examples to follow. All right, so the interest of doing the free energy from the point of view, from the pedagogical point of view of Resurgence, is that, I need to read what's written here, is that now it satisfies a second order differential equation, but which is nonlinear. So there's a term here, f prime squared, that's just what it is, doesn't matter. And so, well, now we could say, oh, yeah, we have a nonlinear second order ordinary differential equation. How shall we solve it? And let's try to do it using the spirit of last time. So we're going to try to first look at the perturbative sector. So it's not too hard to write now a perturbative ansatz for what f might look like. Just something like that, assuming that I can expand next to x small. And then if you do this easily, you just plug it back in and you're going to get a recursion relation for all these coefficients. I'm going to write it once. I'm not going to write any more recursion relations. There will be a lot, but at least let me write one. There will be a lot in today's lecture. So this will be the only one I'll write. So you have a feeling for what those things look like. So up to now, well, it's just a linear recursion, but then of course the nonlinear term, the squared nonlinear term we saw above appears here. Let's see if I can still make it squeeze everything into just one line. Okay, that's what it looks like. So we can proceed and generate data. So we need to find this guy. We just generate data from, of course, and we can sort of start generating a perturbative series. If we do that, we get a bunch of coefficients, these fn zeros that we generate. I'm not even going to write them, of course, but you can put it in the computer again. I think I will share the notebook probably next time, because I want at least the students to try a little bit these whatever quote unquote numerical exercises I will be handing out. I would like them to try before looking at the solutions. And then next time when there will be no more numerical exercises, then I'll put the notebook on the webpage and you guys can see if it will, there's better coding or maybe not. Anyway, so, yes, there's a question. Yes. Yes, perfectly. I mean, this is just, so again, I don't know if you're looking. Let me just, perfectly, that's perfectly possible. Let me just remind everyone that, I'm just following up until next time. I will just be following parts, not, of course, not all, parts of these physics reports that I wrote with Inês Aniceto and Goshke Vazar. So, but I'll be happy. So, it's not going to be any more original what I am writing on the iPad as compared to that. But sure, I can, of course, share all the things on the iPad perfectly. Anyways, so going on. So we produce a lot of these guys, these non-perturbative guys, as I said, not too hard to do it. And then you say, okay, do I have everything? Do I not have everything? What's the novelty here? So it's not by just, again, doing this sort of numerical experiments, it's not too hard to see that there must be something else besides this perturbative thing I just wrote, because you can easily check these Fn guys, they grow factorially fast without surprise. So we have an asymptotic series. Then there's subleading exponential growth. There's more stuff. I will come to more stuff hopefully later in the lecture. And there's a number here. Let me write it like that for the moment. And, playing a bit, it's not too hard to see that A, it's approximately 3/2. We can, in a minute, see that it's exactly 3/2. It's just, playing with numerics, and that number, which is up there, and the reason why I write it like this will also be clear later on, is approximately I times the square root of 2. Of course, again, this will be exact. And what this is basically saying immediately is that, okay, this is a nonlinear equation. I'm not exactly sure what, again, it comes from a Bessel one, so it's not too hard. Imagining I didn't know. I don't know exactly how to handle it. And for sure, we're going to see later, maybe not next time, but on the last lecture, for sure, we'll be discussing all these minimal string theories, which have, highly nonlinear differential equations in the KdV arc, and those are, of course, we don't know what to do with them. So the first thing that we realize is that the perturbative expansion is not enough, and something else is appearing. So an instant on action and a Stokes coefficient around some new sector. So the next natural thing to do is basically just to introduce a trans series ansatz, like we discussed last time. And so I will just say that f of x, maybe I should be looking at something which is beyond perturbation theory. And so it includes transmonomials. Let's write something like that. Well, there's more sectors like this. We will discuss exactly what to do with them. So this is just the first round. That was an A, I'm sorry. Let me rewrite it better. So there's going to be, in fact, maybe I should write some things in different colors. L. So then there's an X. There's L appearing there as well. And then there's just basically an asymptotic series. So maybe the perturbative ansatz is not enough. And what I actually need is something that goes beyond perturbation theory. In here, what I'm looking at is basically transmonomial to the elf power. Then this is just some starting order that appears sometimes. And then there's going to be new coefficients that look like that. It would be the non-perturbative L instanton coefficient, something like that. So if you grab this new ansatz, saying, okay, maybe there's something else, maybe there's transmonomials, and you plug it back into your nonlinear equation, you immediately find, because again, it's not too hard, you find that A, there's two, I mean, it's a second order equation, so it leads you to an algebraic second order equation that just has two solutions, 0 and 3/2. And that beta there, I put it there because it appears, it's 0 in this case. It appears in a lot of other problems so that you remind that maybe there's more to it. So you say, okay, good. So this looks good. So there's the 3/2. So that makes sense with that. And the 0, for the moment, I'll be tempted to say, the 0 doesn't matter. That's just a perturbative series. That's not true. We'll see that later on. But I mean, for the sake of the pedagogical argument, let's just say that and say, okay, fine. Then maybe what I'm really dealing with at the end of the day is just a trans series. So the solution to that equation should look like this. A one-parameter trans series where I sum over all possible multi-instanton sectors with a trans series parameter that's sort of encoding for me the boundary conditions, the initial conditions of that differential equation. And then something that looks like that, times asymptotic sectors, and these asymptotic sectors, of course, are just the usual thing. Okay. So if you recall the example from last time, now the difference, of course, is that instead of having just last time we had just Z0 and Z1, there are basically two sectors in our trans series. Now I have basically infinite amount of those guys, and it's not too hard to see that if I just assume that there's just that this thing would truncate, and I just go and plug it back into the differential equation. Of course, the nonlinear term says, okay, the next guy needs to appear, and the next guy needs to appear, and so on. So that's actually false. And oops, okay, delete operation deleted too much. And so I actually need to have everybody in for the right. Okay. Right. So okay, now let's play with this guy and let's start to see what's going on. I plug this back into the equation and I start producing a lot of data. What is a lot of data? A lot of data is A, we already know, it's 3/2, and it's a bunch of numbers, these guys. I'm not even going to tell you how to generate it. So, I mean, it's recursively, the equation is nonlinear, so I will never know an exact closed form formula for all these guys, but I can generate arbitrarily many of them. I don't exactly recall how many we did in most of the plots I will show you, but it was roughly of the order between 100 and 200, something like that, which is, you know, you can do it on your laptop easily. And so the first thing you find when you start playing with these guys is that all these guys, they basically are of this type. So they're all asymptotic series. So I have a bunch of asymptotic series, all there diverging factorially, and I need to know how to handle these things. So, you know, one thing that we could sort of expect is that, as we discussed last time, the best thing to do when having asymptotic series is just do Borel transforms and see how far can I get doing a Borel transform. So I can imagine doing Borel transforms of all these sectors. These are, these are the non-perturbative sectors. The Borel transforms looks like this. Of course, I never have an exact expression for this because I don't know all the coefficients, but I can approximate it at order n, whatever. And I can even approximate it using Paddy approximates. We also discussed a bit that last time. So if I do just Paddy approximate, this color is not too good. Let's get the brighter color. If I do Paddy approximate, then we'll find stuff that looks like that. We'll call it usually Borel Paddy, okay, of the health sector is the approximations that we're going to have. And if we now play with, let me show you Mathematica for a second. If we now play with, where's Mathematica? There you go. If we now play with the coefficients that are coming out, so this is the recursion, you see it here. I already sort of showed you a bit of what the recursion looks like. This is computing a bunch of coefficients for you. These are the perturbative coefficients, and I can compute the Borel transform. You see here that I'm dividing by gamma, and okay, so here we computed apparently 121 guys. And we're sort of having an approximation. The Borel Paddy as a truncated power series, I'm sorry, the Borel transform as a truncated power series is not a very good approximation. It's better to do this Paddy approximates. Basically, it's approximating the function not by a power series at the origin, but by a rational function. That's called the Paddy approximate. You can play here a bit then later with the computer. And the reason why the Paddy approximate is very good is there's basically two reasons. One is that it's going to have poles because it's a rational function, and the poles approximate very well the branch cuts that we already discussed. So that's sort of giving you a picture of where those log branch cuts are located. And the second thing is that they behave better at infinity, and one has to do usually Borel resummation, which means that we will have to do integrals from 0 to infinity. And so this is better thing behave at infinity. And here we're looking at show the Paddy poles of the 0 sector. And that is 3/2. And we see that there's a branch cut coming out of 3/2. Okay, so that's something you can try to reproduce. And here's the same for the one instanton sector. Remember that there's now a bunch of them. The recursion is written there. We computed 120 guys for the Borel transform. Then we do the Paddy approximate and we plot the poles, and we get a figure that looks like that. So now there's someone at 3/2 and someone at -3/2. And you can ask, what's that guy? We'll come back to that in a minute. But for the moment, just to tell you that, okay, we can sort of have some feeling of what's going on by doing a little bit of numerical toys, games, which are even not very hard to do. All right, so we go back to the iPad and we can keep going. So what do all these singularities look like? So now we know that the singularities are there. We can ask, what do these singularities look like? Borel singularities. Let me put it on Borel plane. Look like. And so, well, next time we will see it derived a little bit more rigorously. For today's purpose, I will just say that resurgence is quite universal. And so the natural thing to assume is that we're going to find something that looks like what we've seen in our previous example, which were the log singularities. And so the thing that actually is going to happen is that if I grab any sector, this is a bit, let me get the brighter color. If I grab any sector and I compute its Borel transform, and I just go and look close to one of its singularities, they're located at k times a with k some integer. What's it going to look like? Well, there's going to be, last time we discussed that there was basically simple pool and the log branch cut. So the simple pools, I don't know if you remember the discussion, but were associated to something known as the residual coefficient. I mean, they're always easy to put back in. So most of the time I just put them under the rug and I just look at, so because, you know, they're just seeing one element of the resurgence of the, you know, of the next sector, just the leading guy in the next sector, whereas the Borel sees everybody else. I think it's a little bit more illustrative. So there's a log branch cut, which looks like that. Then I see the resurgence of the sector n plus k. And this is expanded, sorry, my iPad is so small. Next to that singularity. So you see that clearly I have the n sector looking at the k singularity, and I see the resurgence of the n plus k sector. So always around the k sector. And there's the proportionality factor. Proportionality factor, I will denote it like that. It's a number that tells me how to move from the nth to the nth plus k sector, if you will. And it turns out that this is true for any k, blue is a bad color, any k different from 0. All right, so here's the origin of the name resurgence once again. All right, so we also discussed, let me say a few words about that as well. We also discussed in the linear problem how we could abstract from just the singularities and look at the slightly more improved object, which is known as the alien derivative. That's this object here. And if you recall, maybe we can just do a 2-second recall of what happened last time. When we looked here, this is what we did last time. When we looked at the Borel singularities, here of the phi naught, phi 1, phi 1, phi naught. So this looks exactly the same. So the only thing I'm not showing now in the nonlinear case is the pole. That's always there. It doesn't matter. And I never mind about the holomorphic structure. So that's it. And remember that we abstracted everything to just these two equations. At the plus a singularity, I see the resurgence of phi 1 up to Stokes coefficient. And at minus a, I see the resurgence of phi 1 up to Stokes coefficient, which of course in that case is 1. So it's not too hard to expect that also in this case, something similar is going to happen. And the way it's, again, we'll derive it next time. For the moment, I'll just motivate it by looking at that singularity, is that, of course, the k is the same k. So that's where the singular parts are. I'm looking at the nth sector. And what I find is, okay, let me just immediately do the correct parameterization. What I'm going to find is there's just a numerical factor which is convenient for normalization. And then, yes, let me put this in a different color. And here's going to be a little detail we'll have to discuss. Times, and then I see the resurgence of n-splice case set. So the first thing I want to point out is that I'm handwriting, which means I don't have different fonts. And this guy is not the same. Well, they're related, of course, but as a number, these two guys, in fact, one is green and one is yellow, they're not the same number. So I'm going to put an arrow like that to distinguish between them. You could say, well, but that's just a number. Why are you putting a vector symbol? Because generically in more multidimensional transseries, they will be vectors, whereas the green ones will always be complex numbers. So that's just the thingy. And the green ones, we will call them Borel residues because they're essentially associated to the residue, quote unquote, of the log. And the yellow guys are Stokes coefficients. Generically Stokes vectors here in a one-dimensional transseries. Yeah, that doesn't make a difference, but anyways, let's put it like that. So you could say, okay, I can sort of buy that, but that's by no means a derivation. I agree, I'll do a derivation next time. Let me just tell you, and I'll do a derivation in the one-dimensional case, which is the one that I'm exactly writing for you. But the nth dimensional case is more complicated. So, but let me just motivate where this comes from in a plot. And it's the following. So if we go back to the Borel plane, let me try to see if I can, well, barely include the Borel transform. If we go back to the Borel plane, so this is Borel plane. And we draw a Stokes line. Remember that the Stokes line is a line where there's singularities. Now I have many singularities. So you could ask, how can I resum over all these singularities? And so we discussed last time that there was sort of the left and the right Borel resummations. And if there's a single singularity, so if by any chance this guy's not there, this guy's not there, this guy's not there, so, which was the case in the linear problem we discussed last time. If there's a single singularity, well, I mean, there's S plus, there's S minus, there's nobody else. But in the general case, where everybody is there, there's actually a whole lot more integration contours I can consider. So here's one, here's another, and so on. And so basically the alien derivative is sort of an average over all possible integration contours that you can write down, all possible resummation contours. And that's why the generic definition is more complicated. We'll have there's a simple derivation in one dimension that we can do next time. So for the moment, let's just leave it at that. But I think it's quite motivated from looking at the Borel singularities that this looks exactly like the linear problem we had last time. So it's not a very big deal. You could still ask, how exactly do we relate these two guys, the Borel residues and the Stokes coefficients? Well, that's not, again, I will derive that next time. For the moment, let me just say that it's not too hard to write down a couple of formulae. So it turns out that, let me just write one or two. So Sn goes to n plus 1 is, for example, just numerical coefficient times. So Borel is just basically related to Stokes. And let me write one on coming back, which is also not very complicated. So, I mean, it's not like they're very different. It's just that there's these two numbers that going around, and there will be, today, they're both complex numbers. There's not a lot to say about them. Next time, it's going to be quite important, especially on the last lecture, because it turns out that it's the Stokes coefficients, these vectors, which one can sort of nail down. And the Borel residues, they're more complicated, transcendental numbers that you can find. Let me also say that a little bit hand waving for today, you can see that the Borel residues depend on where I start and where I end. So they sort of depend on 2 points, let's say two coordinates on the trans series, whereas Stokes data are just associated to basically a location of a singularity. I'll make some plots as we go along today to make these things more clear, just trying to give a little bit of an idea. So let's make a plot of all these things, try to make them slightly more concrete. We can write down trend series. Actually, instead of, why don't we just do it first with a plot which is easier to see, which is the following. Let me share physics report so I don't have to draw this. Then I will draw it, but this is on page 21, so maybe I can go here. So we can draw the trend series like that. So I'm going to associate a little box. So I'm going to draw a little chain, well, this is infinite, which are all the asymptotic sectors in my trend series. And the derivations, this is like the plot I made. I'll come back to that in a second. It's like the plot I made for the last time for the partition function. There was just phi naught and phi 1. There was a delta plus a that allowed me to go from phi naught to phi 1. And there was a delta minus a that allowed me to go from phi 1 from phi naught. Now there's a whole lot more possible motions in this chain that I can make. And let's now understand them a little bit better. Where Stokes data is. Let's go back to the iPad. Back to the iPad. It's not connecting. Try again. There we go. So we have, again, the trend series now looks like that. Phi 0, phi 1, phi 2, phi 3, so on and so forth. And now it turns out that I didn't write it here, so let's go back to that question. What are the possible case that I can have? Well, it turns out that for the Borel transform, basically the only constraint is that k is different from 0. I mean, Borel, remember, defines the germ of the function at the origin, so I can't have a singularity at the origin. But for the alien derivative, it turns out that it's slightly more complicated. This again will become clearer next time when we do the one-dimensional derivation, is that k is smaller or equal than 1. Of course, it's still different from 0. Same requirement applies. So these are the requirements. So I basically have sort of one motion forward. Let's do this. So I have one motion forward. That's all I can do. But then k equals 0 doesn't exist. And then I can have lots of motions backwards. So I can have, let me draw in different colors. So I can have just, again, one jump backwards. Or I could have things that look like jumping twice backwards. Let me draw one more. I'm jumping 3 times backwards. So there's many backward motions. And they're associated with different Stokes coefficients. So the motions forward, I just have S1. Let me put an arrow on them to remember that is now I'm just looking at Stokes coefficients. But coming back, and so that's just one Stokes coefficient. And by the way, that's a Stokes coefficient which people have computed a lot, in fact, since the 80s in many string theory and matrix model examples. But that's just a part of the story. So there's a whole lot more people going around. And so there's this, actually, I should have corrected this. This is actually, let me, how shall I correct this? There's actually nobody coming back to the origin, of course, to the first sector. So let me just remove those guys and draw it. These guys like that. Sorry about that. And there's one that comes from over there. So this guy, of course, jumped 3 times back. This guy jumped 2 times back. And these guys are just jumping 1 time back. So there's and everybody should have arrows on top because they're all Stokes vectors. And so what we see is that, well, there's a lot of numbers that I actually, so the yellow numbers are not enough. I need the red numbers, the green numbers, the blue numbers, if I really want to describe every possible Stokes transition that my trend series may undergo. And so, and the yellow numbers are sort of quote unquote easy to calculate, at least they've been computed in many examples for a long time. But the red, green, and blue numbers, they're much harder to find. Of course, in the example that we're now discussing, it's not going to be very hard. They're all easy. But if you, I mean, look at some sort of, even the polynomial equation that we'll discuss next time, maybe the other time. Up to, you know, a few months ago, nobody knew what the non-yellow numbers were, except numerically. So we had a lot of numerical evidence for them, but we didn't know how to compute. Now we know how to compute all of them. So the structure is a little bit more intricate than may look on a first round. All right. So what else do I want to say? So that's basically it. So we have, let's call the yellow guys, let's call them forward motions. It is just on, let's call this the alien chain. Just nomenclature. It's not very important, but I may say these words later on. And everybody else, we'll call them backward motion on this alien chain. And okay, we want to understand all these people. So the first thing we may ask is, okay, that's looks like highly formal. Why would I even care about that? So let's just discuss this in a moment. Why is this relevant? And the reason why this is relevant is basically what I've just said. We need connection formulae if we really want to describe our observable, whatever we're computing. In this case, this simple example, it's a free energy, everywhere on the coupling constant complex plane, not just in some regions. So there's going to be wedges where the asymptotic approximation that we start off with is good, but as we cross Stokes lines, that asymptotic expansion is no longer good because other terms in the train series may take dominance. So we need to be following all of them. So let's look a little bit at Stokes discontinuities in this language. Stokes discontinuities. So what we discussed last time was that there's basically this transition at 0, and there's a transition that could exist at pi. And if you say, wait, are we sure that's all there is? Let me jump again. Again, this would be much faster live because the computer would be projecting Mathematica. And you can see that for the perturbative sector, yeah, all I have here is the 0 direction on the Borel plane, is the Stokes line. But as soon as I start going to the 1 sector, and by the way, this is true for all others, you can make lots of these plots if you wish, and I recommend that the students try some of them. I have singular directions along 0 and along pi. So I do need to consider Stokes discontinuities along 0 and pi, both of them. All right, let's go back to the iPad. So I have the discontinuity along 0 and the discontinuity along pi. And we discussed last time how to write them. So I'm going to write this for arbitrary sectors n. Now I have an infinite amount of sectors. Remember that when we did z last time, just had z0 and z1. We wrote them very easily. Now it's a little bit more complicated. So going forward, all I have is a single singularity. So I just have to consider this guy. Going backwards, I can have a lot of singularities. So you can see, fortunately, it doesn't fit. So I only have a possible motion forward, which is these motions I've already discussed. And I can iterate them. So I can keep going, because the train series is infinite, goes all the way up to infinity there. So I can just keep going. And so this exponential is going to be, there's a single guy, but once I, power expand the exponential, I have arbitrary numbers of alien derivatives. Going back is slightly different because remember my train series basically ends coming back in the perturbative sector. There's no negative instanton, not here. We'll discuss that later on. So there's only, if I start at some sector, I can only come back like that or like that. So there's just, I can keep going back eternally. So what's going to happen is that up here in the argument of the exponential, this is going to truncate, and it's going to truncate at n, exactly. Okay. And so this is what I have. All right. And then the discontinuities themselves, of course, remember that the discontinuity at theta of phi n is basically just phi n minus the Stokes automorphism. So I have all of that. So let me just write down explicitly two examples, just so that we get a feeling of what's going on. Let me write down one example along the zeroth direction and one example along the pi direction. Okay, so let's compute this guy. And so it's not too hard to see that I'm going to have the exponential keeps going, as I just said. So I keep getting guys like that. And let me not write everybody. So then I get delta a squared, then I get delta a cubed, and so on, collecting on phi 2. And if you do the calculation, what this is going to be is just going to be phi 2 plus, then there's going to be a Stokes coefficient. It's sort of, yeah, let me just write the formula and then we can see. There's, of course, some factorials that come from the exponential. Let me write once more. And then there's, of course, the guys that come from Stokes data. And so what you can see now, we can compare these things. So we started at this 2 sector. So up here, we're starting at the 2 sector. And we can move once to phi 3 or twice to phi 4. So we moved once to phi 3, and that's the coefficient, the Stokes coefficient, which is relevant. Or I moved twice to phi 4. So in fact, there's an S1 squared. Or I moved 3 times to reach phi 5, and there's an S1 cube, and so on and so forth. So I can write all these guys. And it keeps going and going and going. What happens? So that's one example. Let me give you another example coming back. Let's compute phi pi acting on phi 4. You know, if I do that, again, I have, let me not, okay, I can write down the exponential. The exponential is going to look just so that, so the only number of guys that I can have here going back, so this is just a linear term in the expansion of the exponential, can only go up to 4, or else I sort of would get out, quote unquote, of my chain. And then there's, of course, quadratic and so on, phi 4. And so when you do this, you get phi 4, then plus 3s minus 1 exponential phi over x. Phi 3. So you see, what is this guy? This guy is coming from phi 4. So I'm somewhere here, and I just do a jump. So that would have been phi 4. And I just do a jump coming back to phi 3. And so that's the term I have. Then, let me put it in another line. I have this next term that looks like this. So one has to be, there's lots of combinatorics and so on that I'm not exactly telling you how to compute all these numbers, but they just come basically from exponentials and alien derivations. And now you see, okay, so coming back from phi 4 to phi 2, I have the correct exponential weight there, but I have sort of 2 contributions. So I have one contribution just s minus 2, and I have another contribution which is 2 times s minus 1. Not too hard to see what's going on, right? If you go back to the chain, so I'm somewhere here on phi 4, and I'm coming back to phi 2, so I can just do one jump. So that's 2s minus 1, or I can do a full s minus 2. And because now there's these 2 jumps, the contributions are more intricate. So there's the single s minus 2, and there's the double s minus 1, and so on. And quickly, the combinatorics becomes horrendous. But I mean, it's very simple to do this, you know, at least in the computer. If you just want to generate data and data and data, it's not very hard. But you need to see how to do these guys. Let me make one more comment, which is that if instead of, so I wrote down everybody here in terms of the Stokes. No, there was nothing there. So it was just these 3, and up here, these guys. Of course, there's a much simpler way to write this, which is in terms of the Borel residues. So again, let's just remind ourselves that I sometimes will be using the Stokes coefficients that appear in the alien derivative. Sometimes I will be using the Borel residues that appear next to the singularities of the Borel plane. And if I do that, then we can keep going with this one. This has the simpler way to be written, which is just going from 4 to 3, going from 4 to 2, and try to put everybody together, going from 4 to 1. There's nobody else. So you see that in terms of Borel residues, this is what it looks like, and it truncates. So that's, let me put here, plus 0. That's it. It truncates. That I can't go further back from the perturbative. Well, in fact, I don't even reach the perturbative because the Stokes coefficient there would vanish to 0. And so what we see is that that guy there is basically that guy there. This guy here is this guy here, and that will be another one that I didn't write down. Okay, so all these things appear, and so the punchline is that even though we were a little bit discussing Borel singularities, and that might have looked a little bit formal, why am I discussing all these Borel singularities for these objects? And there's these coefficients, either Borel residues or Stokes coefficients that I need to play around with that might look a little bit abstract. In practice, you know, all these quote unquote motions on this quote unquote trans-series chain are basically telling me about Stokes discontinuity. So it's basically telling me about connection formula. And only when I know everybody can I be very explicit about connection formula. We will also see today that only when I know everybody, I can be very explicit about large order relations, which is one way we have to try to access part of this data. All right, so that's the idea. Now, let's take a better look at the Mathematica notebook again. Where is it? Here. So we were looking at the Borel plane of the one instanton sector. We saw, well, there's a singularity at plus A. There's a singularity at minus A. This seems to be a little bit not what I would expect from the plot that I've just done of the alien chain. When you look at the alien chain with Stokes coefficients, I see that if I'm in the one sector here, I can move forward to the two sector. So there should be a plus A singularity, but this guy's back is dashed. Basically, the alien derivative tells me I can't move back. So why do I see a singularity back here? And I mean, if you thought about it from scratch, you would know. In fact, you might remember that we already computed the instanton action exactly, and there was a 0 in the treehouse. That's basically the 0 that's coming into play. The reason why I chose to do this in sort of slightly contrived way is to be pedagogical, because in very deeply non-perturbative problems, you may say you don't have this feeling what might be there, what might not be there. You have to play a little bit as you go along with what you're seeing, what you're expecting, and how to put all these things together. And so this is just basically a pedagogical comment or a pedagogical detour to try to see how those things happen. So let's, yeah, I think I have 5 more minutes. So let's just see before the break. So let me just do this. Let me share the iPad. Whoops, how do I share the iPad? Here we go. So if there's a motion backwards, so again, let me just write it back down. So there's phi 0, there's phi 1, and so there was this, so this has a plus A singularity, and this guy had plus minus A singularities. So this is telling me that the ansatz I first wrote down was not enough. It could see a part of the non-perturbative structure of the problem, but not the complete non-perturbative structure of the problem. And then you can say, okay, then I need something else. This is something that happens a lot in practice. I find new sectors I was unaware that existed, but they're there controlling, Borel singularities, large order growth, everything. So the reason for why this apparent discrepancy that mostly pedagogical occurs is because we had already computed that a is 0 and 3/2, and I sort of said, okay, let's forget that and let's just look at 3/2. No, we can't forget that. That guy, the 0 will also, it's a not very complicated sector. In fact, it's going to be an almost trivial sector, but it's coming into play. So actually, I don't have a single instanton action. I have 2 instanton actions. One of them is trivial. So what do I do now that I have, and by the way, that's also not very unexpected because I started out with a second order differential equation. So I sort of naturally expect to find 2 train series parameters. I mean, I need to have, you know, the space of solutions is 2-dimensional. So then I'm going to say, okay, so my initial 1 parameter train series ansatz were not enough. What I actually need to do to look at the full solution is have 2 train series parameters, sigma 1 and sigma 2. And so the train series is now going to be written in this way. 2 sums over these 2 parameters times exponential, it's not going to fit. Let me, times exponential of minus NA over X. Well, the second A is 0, so there's no MA over X times some sectors, NM. Okay, that's what the 2 parameter train series is going to look like. This should include now everybody. Well, maybe there's extra surprises. In principle, no, because the equation is second order, and there won't be. But and all these guys are asymptotic series, which I am now labeling in this way. And so, sorry, that's okay. And so you see that now I have 2 train series parameters. There's these NMs which appear. They're associated to the 2 train series parameters, but there's basically a single guy appearing here because remember that the only non-vanishing instanton action is that one. And so yeah, I could write here minus m times 0 divided by x, which I just forget. And so looking at these plots, looking at where are singularities on the Borel plane, we'll discuss a little bit in the second hour. We'll discuss looking at large order relations. We can sort of, you know, digging deep into perturbative asymptotic expansions. We sort of see all this resurgence of all these sectors, even some that we could have not expected to be there to start off with. So this is the 2 parameter train series. Let me rewrite it in a slightly simpler way, because so that once everything is washed, let me not go through the details. You can see all the details in the physics report if you want. This can be written in a very neat way in this way, because one of the instanton actions is 0. That's basically. So this is what we had already seen. That was our first guess, but we actually need a second sector. The second sector is almost trivial. The reason, by the way, there's of course a trivial reason why the second sector is so elementary. Whereas here we go. Here's the differential equation we started off with, and if you look, f of x never appears. So this is actually a differential equation for f prime, and so that's why there's just a constant that needs to be added in. And that's what it is. So we have sort of the 1 parameter usual nonlinear train series, and we need to add a little constant. But this is actually quite pedagogical because now it's telling us how the Borel singularities and the alien derivative are changing, because now the Borel transform around any n0 sector, and let's just expand it next to the kth singularity. It's gonna be what's it gonna be like? In fact, I can just try to put the yellow in. It's gonna have a log singularity. Let's immediately write the log singularity. Well, now I'm expanding around x, or s is already next to k plus a. That's why only s is written. And so what I find then is what I had already seen. But there's a novelty that comes from that constant term. And so there's sort of s tilde you can only come back to 0 with this S tilde times, it's too small. Borel of phi 0, 1, that's the sector I hadn't seen yet. Okay, there we go. And this is this holds for k different than 0. And you say, okay, so there's a blue novelty compared to what I had seen in green. So I can, and again, this is something that you do in practice when you're doing Poivet, Yang Li, and all these more complicated systems in the KTV hierarchy. You're sort of seeing as you go along if I need to add in anyone else or not. And you see how the Borel singularities and the alien derivatives are changing. So let me just get like 3 minutes before the first hour finishes. Let me just write down the alien derivative, which I do in analogy with what I've done before by just comparing against the Borel singularity. Okay, so this is what I had already seen. And I have a novelty, which is just this guy. Okay, and I should put an arrow on top of these things to remind you that those numbers are not the same ones are. So don't forget these guys are. So, okay, let me just say that this is for k 0, and here I have Stokes data, and here I have Borel data. And so just to finish this, let me not even do the plot myself. Let me be slightly lazy and just share the plot that you get, because it's much better than with LaTeX. And so here we go. So this is what we had before. We knew how we could go forward. We knew that there was many ways to come back. So there was sort of forward motions, backward motions, and now let's say quote unquote sideways motions, because I can still go to this last sector. And so playing a bit with this Borel analysis, we started off trying to find a solution to this nonlinear free energy problem, which told me that, well, there's an infinite trans series. And we sort of started guessing that that's all there was. And then looking at the Borel plane, we said, oh, there's somebody else. And so the whole structure is more complicated. And of course, I'm not going to write down, you can look up the report if you want. I'm not going to write down examples of connection formulae, but there's going to be a whole lot more complicated and so on. And so this tells us that this analysis can sometimes teach us something about non-perturbative sectors that we were sort of naively unaware of. Okay, so I think this ends the first hour. It's I think we started at 05, so it's 05 again. And well, Ricardo can tell me if there's the 15-minute break now, I guess. All right, so what have we done in the past hour? Very simply, we continued from our very simple example of last time, which was a linear equation for a quote-unquote partition function. We started looking at a nonlinear problem for the free energy, given by that term there. And what we did over the hour was to see how to construct the trans series, which actually involves two instanton actions that's associated to the differential equation being of second order. And well, we discussed Borel singularities and their equivalent rewriting in terms of bridge equations. And the reason why we introduce all this, of course, is to write down Stokes discontinuities and to be able to extend our solutions, our asymptotic solutions, everywhere on the complex plane or on the real line when we're doing more physical parameters. And then by looking at Borel singularities, we said, okay, look, hang on. My initial guess, which was basically this one, for the trans series is not enough. There's Borel singularities already telling me that actually something else appears. And so we're learning from an analysis of the Borel plane, okay, in a simple example, how to reach the full non-perturbative structure of our solution. And what I want to do in the second hour, second half, is to do the same analysis, but now looking at large order. So I think there's these two classical approaches to trying to figure out the whole non-perturbative structure. One thing I should say before going on is that we always need, especially for large order, Stokes data. And Stokes data, which is always, I mean, everything is always encoded in a plot like this. Both the discontinuities for the connection formula that I already wrote and the discontinuities that will be useful, which are the same, which will be useful for large order, which I will discuss now. And so knowing these numbers is a hard question. And I will discuss them next time, or maybe even only on the final lecture in Paris. For the sake of our example here, I'm not going to discuss it, okay? All I'm going to say is that in this problem, it's actually, so generically, it's quite hard. This problem, it's actually quite easy. Why? Because we did this last time. We computed Stokes data for Z, and they imply Stokes data for F. Okay, so we will, I mean, there's a whole section that I will leave as just a reading assignment for the students, which is this section 2.5 of the physics report, which tells you how to compute the Stokes data of the free energy out of Stokes data partition function. If you want, it tells you how out of, can I find them quickly? Yes, out of, these were the Borel singularities for the partition function. There was a factor of 2 there. There was a factor of -1 there. It tells you how out of these two numbers you can find, for example, the square root of 2 that I already mentioned that appears, that we'll now see appearing, okay, and other numbers that appear, okay. I'm not going to go through that. It's actually quite simple. It's generically, you don't have this possibility. I mean, it's a research question whether there is some sort of quote analog of the partition function that will solve this problem for us or not. Maybe, but we don't know for sure yet. So for the moment, it's just something that occurs in this simple problem, so it's not worth discussing in much detail. So let's just assume that we know those numbers and we want to double check. Okay, so having said that, let's just put here Stokes data. Let's assume for the following 15 minutes, 45 minutes, whatever it is, that Stokes data is known, and then we're just double checking that everything is okay. All right, let's just work under that assumption. All right, so then we'll do next is look at the large order behavior of all these people. All right. So how do we do that? Again, it's basically the same that we did for, but let me write it again. For the partition function, which is just basically use Cauchy theorem to try to obtain some sort of dispersion relation. So we look at the discontinuities of along theta of some f. F will be any sector of the train series. So F is basically going to be any of these sectors. And what I'm going to have is discontinuities that we've already seen when theta is 0 or pi. Of course, if we're looking at the perturbative sector, it's only along 0. The higher order ones will have both 0 and pi. And now the Cauchy theorem that we already discussed last time, how it goes. So I'll just give you the formula. It's going to tell me that I can write down a dispersion relation that looks like that. So there's going to be an integral along theta equals 0. So this is the zeroth discontinuity of F. And then there's going to be another integral along pi of the discontinuity along pi. So that's just it. I mean, this is a straightforward generalization of what we did last time. All right, so can we write down some large order relations? Let's start with the perturbative sector. Let's illustrate in detail. I'll also do the one instanton and the two instantons, but I will go in detail through the perturbative, and then the following ones are very similar. And again, I insist that the students should try to reproduce these plots. They're actually not so hard. Basically, once you generate data, generating the plots, I will show you. It's quite straightforward. There are some sort of numerical techniques I'm not going to go into that accelerate convergence and so on. But yeah, so you should try to reproduce all these things, and then next time I will this notebook that my student Roberto has done to sort of support this work. I will make it available next time. So let's try to first do the homework and then look at the solution. All right, so let's start with the perturbative set. Which is phi not, and you just plug it. Sorry, actually that one does not exist in the perturbative. You just plug it over there. So this guy is not there for the perturbative, and see what happens. And it's not too hard. So I'm just reproducing the calculation that we did for the partition function last time. That just I'll write it again. So this is what you get on the left-hand side. You just plug it in. And on the right-hand side, you now have a sum over all these Stokes coefficients. I'm putting the arrow there to remind you that it's not a Borel residue. And then I have to do this integral that's going to give a bunch of gamma functions. Sorry, there's a fraction here. Times this sum. That's an H. All right, so it's not too hard to see that there's an exponential of W, there's a fraction of W that I will expand, there's a W, so I'm basically going to get a bunch of gamma functions. And at the end of the day, let me not do, so this we already saw last time. So what you get at the end of the day is the following. The coefficients of the perturbative series, I'm going to move the exponential growth to the left-hand side, and I'm also going to move the subleading. So I have the leading factorial growth, and which I move to the left-hand side. I have the subleading exponential growth, which I also move to the left-hand side. And on the right-hand side, I'm just leaving stuff I want to compute. So what you're going to find is something that looks like this. I'm going to write the whole expression so that we see everybody that comes into the game. So these are all terms which are power suppressed in 1 over k. 1 over k, 1 over k squared, so on. And then that doesn't stop there, because I can keep going forward. So basically, if you want, let's just start by looking at what we've done. So we sort of remove the factorial and the exponential growth. They're always there. So we just conveniently package them on the left-hand side. Then Stokes data. There's one guy there. That guy I would like to know. And then I start seeing the resurgence of the one instanton sector. At 3 level, the one instanton sector, 1 loop, power suppressed 1 over k. The one instanton sector at 2 loops, power suppressed k squared, and so on. What about the 2 instantons? Yes, the 2 instanton is also there. So that's the next guy that appears. It's exponentially suppressed. Then you get this S1 squared. And you get something that looks exactly the same, with a 2a instead of an a. Because we're now finding, can I put everybody here? Okay, maybe I shouldn't write anybody else. I think it's enough to illustrate what's going on. And so on. And then if you were to find more people, they would be still exponentially suppressed, okay? So what I'm saying is there's a new Stokes guy there. Actually, in this example, it's not new because it's just a square root of the first, so, but it could be something else. Things are now exponentially suppressed the 2 instanton sector is exponentially suppressed, then there would be the 3 instanton and the 4 instanton and so on. They're all exponentially suppressed. And I see again the resurgence of everybody. So I see the resurgence of the 3-level 2 instantons, the resurgence of the 1 loop 2 instantons, 2 loops 2 instantons, and so on. So out of this formula, I can extract all non-perturbative content out of the perturbative series. It could be arbitrarily hard because I need to dig arbitrarily deep into the asymptotics to find everybody. Of course, this completely agree. But in principle, they're all there. They're all seen. It could also be that there's non-perturbative sectors that I don't see immediately in the perturbative asymptotics, but I only see in some nth instanton asymptotics, and they would be iteratively reached in this procedure by decoding the 1 instanton, decoding the 2 instantons, and so on, and then out of the 1 instanton decoding more people. So this can also happen recursively. So to this kind of structures we call, all right, so that's the formula. Let me leave part of the formula there. This we call a large order relation. And we see that there's different contributions. There are contributions in 1 over k. There's contributions in n to the minus k. And we need to sort of decode all these people. So how can we start looking at them? Let me do, which example shall I do? Now I want, okay, let me first write it and then look at the computer. So let's extract just the leading part. Let's imagine that I have all these coefficients. I got them from the perturbative series, and I want to compute that guy. Is there a question? Yes? Yes. I'm sort of jumping. Yes, of course. I mean, you can immediately extract AK. So I'm sort of jumping ahead of that. So out of the FKs, obviously that the first thing that you have to do is to check, and this you can do numerically, check if the radius of convergence, remember, when was it? That was probably the first thing we've ever done. The first thing we ever did for in these lectures last time was to see that things are asymptotic, so that they have the 0 radius of convergence. So one thing you can do is you can sort of compute ratios of the coefficients and try to see if they asymptote to 0 or not. And then if they do, then you say, I'm playing with an asymptotic series. And then, of course, you look at other adequate ratios. Can I go back to where we were? Yes. Then if you do that, you can say, this guy is growing factorially fast. And then the next step would be, okay, what is the exponential growth? And I can do sort of another ratio where I kill the factorial, that I do the adequate ratio with the FK, whatever it is, and I extract the instanton action. So I'm sort of assuming that those two things have already been done, because we sort of did, okay, maybe it was the last thing we did on last time, when we were looking at the asymptotics. So this is the before we started today. So this was the last thing we did last time, was to look at the growth of the Z coefficients, and I sort of showed the plot where we could extract the factorial growth and the exponential growth. So now for the free energy, I'm sort of assuming that these two things we've already checked, and I'm starting to check the new things. If that's not very fresh in your mind, what I can do is just quickly go back here and show you that plot. Actually, let me go straight to the Mathematica file and show. So this was last time. Where was it? Where is it? Somewhere here. Yeah, here. So we looked at the coefficients, Z0 coefficients, and we were looking at how they behaved. Okay, so this is how we ended last time with these Richardson transforms. So I'm sort of assuming that this has already been seen, and in fact, what I want to do now is going to be similar plots. Here's a preview. I will discuss how to get to this plot soon of the free energy. Is it clear? Okay. All right. So then let's go back to the iPad. Okay, and where are we? Here we are. All right. So as I was just replying to Ricardo, we're assuming that we already know those guys. So now so this is now a sequence in K. And when K is very large, this guy is immaterial, this guy is immaterial, and so on. So when K is very large, I should be finding this number here. So I can try to see what does it asymptote to. And remember that in general, it asymptotes to a number that I don't know, and it's hard to compute. And so this is sort of a prediction of Stokes data, which I need to write down connection formula. So it's one way to access them. You could say it's a way I don't really like because it's numerical, and I would totally agree. But sometimes it's the first approach you can do is just grab some numbers. Then you try to understand them better analytically. So this is we've done in some examples. But when you have nothing, yeah, you better have some numbers, even if they're numerical and less elegant. And then you sort of try to find the analytic formula that they're constructed. So this is sort of the dirty part of this procedure, but it's one that you have to suffer through so that then you can sort of understand what exactly is all the structure that you have. All right, so let's look at, let's plot this. Now, I'm sorry, now I need to jump in between the iPad and the Mathematica files. So this is slightly inefficient, but well, bear with me if you will. All right, so here we have now the free energy, and we're sort of computing this coefficient. So there's we're going to do, yes, figure 12. So we have to compute these Fs. There's the recursion relation here. You might recall the recursion relation. And it seems that we're computing 124 guys. And we're plotting, well, I will flash this briefly and I will let the students then try to plot this. We're plotting the sequence. The sequence is this thing here in red. And we know it should be converging to something, well, the imaginary part or whatever it is. It should be converging to, I guess in this plot, to minus square root of 2. Is there the minus square root of 2 here somewhere in the A equals 3/2? Okay, I'll let you, here we go. That's what it should be converging to. So we're looking for that number over there, which is this purple line here. And the first thing you would say is when you look at these red dots, you say, well, it's going there, but it could be going somewhere else. So can I slightly improve this? So I mean, I'm just going to say one word about it, which is yes, you can slightly improve this. This is it's a technicality, but it's just so that I need to share the iPad first. It's just so that you are aware of that. There are sort of two numerical tricks. One is no, I went back to mathematics. I'm sorry. One is really technicality, which is acceleration of this asymptotic series. And the other one is less of a technicality, which is Borel resummation. All right, so the first thing, I'm just going to make a micro comment on that. Then we go back to, which is Richardson transforms. And what they do essentially is if you have a sequence, let's call this a sequence in K, which, well, is, maybe I should write asymptotically to a number plus corrections in 1 over K plus corrections in 1 over K squared, and so on. There's a method that sort of iteratively, I'm just going to draw it schematically. And then I recommend that, I mean, you can look it up in Wikipedia. It's probably even better explained than in the physics report, or just look at the physics report and you see how to implement it numerically. I mean, it's really written there. I'm not going to be saying a whole lot more to it. But schematically in a drawing, what's going to happen is that when I do a Richardson transform of this sequence, I basically am going to kill the 1 over K guy, so that the first correction is going to start at K squared, and I'm going to get this guy slightly better approach. And then I can do a second Richardson transform of that guy, put here a 2. I'm going to kill this guy as well, so I'm going to start now at order 1 over K cubed, and this guy is going to be even better, and so on and so forth. So then I'm sort of improving on the limit of the sequence by doing these resistance transforms. And you can see the algorithm, it's written in this report, or just browse it on Wikipedia. It's probably much better explained there with lots of examples for sure.
Ricardo,
and so, yes?
Just a comment.
Yes, please.
You can be much more efficient by taking the formula with two terms at once.
Yes, definitely. Definitely. So
the problem is that you don't know what it is 1/k, which is good, or 1/k.
Jean, I think your sound stopped. I'm not sure if you wanted to stop as well, but your microphone is muted. Let me supplement what Jean was just saying by looking at just flashing the formula for the algorithm, which is here. And so basically what you see is that we're sort of killing the kth guy. And what Jean was saying is that we can try to kill more guys. I mean, for sure, there's many efficient algorithms to do this. There's closed form formulae. So I think that I'm really putting under the rug a lot of people. What I want to, yes. Not infinite precision. I mean, there's always. Yes. So as definitely. Yes. Let me go back to the Mathematica so that we can actually, where's Mathematica? So that we can see how this game plays. So here we see that was the original sequence. And then I'm not sure if this is just 2, because in the primer, I think we did 5 Richardson transforms. I'm not sure if this is the 5th or not, but you can see that the improvement is quite, the green is better than the red, and the blue is even better. And I'm not sure I can zoom in on this. Yeah, I think it's like that, right? So I'm zooming in on the graph, and what you're seeing is that as we do Richardson transforms, we have, I mean, we lose some guys, right? So I think blue is probably the 5th guy because we already lost 5 guys. So yeah, so there's lots of issues of precision. I totally agree. I'm not going to go into any of that. I'm just going to tell you that this is one way to access numbers. For example, I can tell you that in the polynomial cases, that this is how we sort of started this problem a few years ago. We had numbers that we could numerically write down with almost 100 digits. So I mean, the precision, I would say that when you have almost 100 digits, was pretty good. Yeah, we couldn't guess it back then. We know what they are because they're highly transcendental. But you know, you have to play with this and you know, get dirty in the details of the numerics. Totally agree with that. Anyways, so if we play this game, let me. This is what you do, and there's more plots that you can do. I'm not going to show you more of the Mathematica code. I'm just going to show you the plots themselves. So let's go back to, here we go. This is the plots are on page 35. Page 35, here we go. So here you can see that I am computing here on the left, that number, minus square root of 2. That's, if you want, the first Stokes coefficient. And in the right plot, sorry, I don't know what's, in the right plot, I'm computing this contribution here, which is the contribution. So you see, this is the Stokes coefficient times the 3-level guy. And this is the Stokes coefficient times the 1-loop guy. And I'm finding that number. And again, it's sort of matching. So I'm, you know, in an inefficient, not elegant, quite dirty way, I'm reproducing the one instanton set, step by step. And this can be quite laborious. And most of the time, we're not terribly interested in reproducing the non-perturbative, the 1, 2, 3, whatever instanton sector we're looking for, because those are recursively determined once you plug in a time-series ansatz. What we're interested in knowing is basically Stokes data. Stokes data is really the hard part to find. And if we're doing these tests, we're doing these tests for two reasons. One, to validate the time-series structure, which could, as I already shown you in a different example in the first part of the lecture, could have also been seen by looking at the Borel plane singularities. So we're sort of validating the time-series structure. That's step one. And then when we were sort of confident that the time-series structure is okay, then we need Stokes data, because without Stokes data, we can't move outside of our starting wedge, if you want. We need to, Stokes phenomenon is really the juice here. So when we actually compute a number like that, if we're saying, ah, look, but the tree level and the one loop guy are both right, we're just we're doing this to validate that S1, which appears on both cases, was right. We're getting more data and more precision on computing S1. In this case, it's particularly simple. It's square root of 2. As I will show you next time or in the fourth lecture, for Ponleve, they involve zeta numbers, arbitrary zeta numbers. So it's a sum of zeta numbers. It's quite nastier than this. Okay, so that's one example of plots. Let me show you another example. Let's go back to the iPad. Okay. So I strongly recommend that you look at the physics reports, that you try to play one or two of these plots, and then next time I'll put the notebook available and you can sort of see the solution to these quote-unquote homeworks. All right, so the next thing is say, okay, we go back here to the large order relation, and you say, okay, the A and the factorial was sort of last time, and now we've seen how to compute this guy, we've seen how to compute that guy. You see that was the F1 times A times S1, and you can iterate and compute that guy and so on. And then you can ask, okay, that's fine. How about the 2 instanton sector? Can I see the 2 instanton sector? Well, in order to see the 2 instanton sector, and in particular, to compute this coefficient here, which would be Stokes squared, I need to remove all these guys. Removing that guy from the right-hand side was easy. Just move it to the left-hand side. It's a multiplicative factor. This is an additive factor. So, and it's an asymptotic series. So I need to first resum this in some way, and then remove it from the left-hand side. And then I will be able to see 2 instanton suppressed people. By the way, if I would want to see 3 instanton suppressed people, I need to resum the first guy, I need to resum the second guy and remove both of them. So this quickly gets quite intricate. So again, let me just give you one numerical comment on Borel-Padé resummation. To sort of motivate how this goes about. In fact, if I want to do it exactly like I did before, first I show you the plot and then I tell about the intricacies. So let me do it the same way, just so that. So implementing resummations, here we go. So there's as you'll be able to see, so we really need to sort of deal with resummations before. And there's some long coding that needs to be done. It starts to get way out of my comfort zone. So please don't ask me details on coding. As I said, I'm very bad, certainly cannot do anything as elegant as Roberto has done. You're going to start seeing that resummations get becoming a little bit trickier. This is the Padé poles, Borel-Padé poles. I'll get to the formula in a second. And so there's resummations, there's integrations that need to be done on the real line that I really can't do. So I'm going to have to be doing some lateral Borel resummations. They're going to introduce some imaginary coefficients that I need to handle. I will explain that in a second. And I really need to suffer through the resummation before I can finally make a plot. And as you can see, Roberto wrote here, do not run in real time. So these are things that actually take some time to implement. Okay, so let me now give you one word on the method. iPad. And then I'll show you the plots. Okay, so on the iPad. Here we go. Okay, Borel-Padé approximate. So I just want to say 2 quick things. The first, so we had that sequence. We're still dealing with the sequence, right? Because remember, now I want to remove this sequence from the large order relation so that I can sort of access the two instanton guy. So we had that sequence, and we're going to Borel transform it. And that would be it. Only that it's not it, right? Because I don't have access to all these coefficients. This is a nonlinear problem. I don't have closed form formulae for all the coefficients that appear. I can only find so many. And so basically what's going to happen is that I cannot go all the way up there to infinity. So I can only go up to, we usually write 2n. That's because of what's coming next instead of 2n. And so that means also that I no longer have an equal sign. Let me put this in a different column. I no longer have an equal sign, but I have an approximate sign. So the best thing that I can do is sort of get an approximate Borel transform. As a power series, this is not very efficient because it doesn't see the poles. The poles are quite important for resummation. You know, I can't go with my integration contours to the poles. And it's also not so well behaved at when t is large. And so a more convenient way, which is well behaved at t small, t large, and sees the poles, is another approximate, which again, I'm not going to get a lot into, and Wikipedia will tell you everything you always wanted to know about Borel by the approximates, but we're afraid to ask. So please go ahead and check it there. I'm just going to write the formula just for the sake of. So BP is Borel Padé. Basically, I'm doing a Padé approximate to the Borel transform of S is basically a rational approximation. L equals 0 n. And you see, both denominator and numerator are of order n polynomials, and hence why we chose 2n. Just for convenience. This is also known as a diagonal by the approximate. You can do non-diagonal ones. Sometimes non-diagonal ones are useful because, you know, of course, whenever you see poles of these guys, these are approximate poles, not necessarily they're, you know, real singularities of the Borel transform. So you need to play a little bit with this, changing the order to see that sometimes numerics produce for you spurious poles and they need to go away and so on. Anyways, so you can construct this guy, play a bit with it, and then eventually you want to do, at the end of the day, what you really want to do is Borel by the resummation. So you still need to do a resummation of this guy. And that's the number that you're going to extract. Remember that is integral from 0 to infinity in dt exponential minus t Borel by the n of x. You still need to do that integral. That integral is also evaluated numerically. So I mean, there's this is when things start getting a little bit dirtier. Anyways, so I'm not going to say any more about these numerics. It's also not necessarily, well, at least to me personally, it's certainly not the most interesting thing. It's something you have to suffer through on your way to finding the analytics. But at the end of the day, what's going to happen is that you're going to produce. So you had this sequence. You will be able to resum this sequence, and I'm going to extract one from the other. Okay, so let me rewrite it here. So I had my sequence, which was this one, and then I extract the Stokes coefficient times the resummation of Borel Padé, and so this is sort of the approximation I have of that first sequence. Well, for some reason, I'm copying what the primer has. It called it chi, which we didn't, but let me just leave it like that. And this is going to be approximate to, and here's the S1 squared, F0 2, 0, plus F1 2, 0, 2a divided by k, plus so on and so forth, plus order 3 to the minus k. Okay, so you see that these guys I knew. These guys, well, I have to do some dirty numerics to get them. So these guys are okay. These guys, well, sort of okay. And then if you kind of do that, then you will eventually reach that guy, and that guy, that 3 level, and that guy, 1 loop, and so on. All right. So that's the idea of the procedure to find the next guy. So let me show you in Mathematica what it was. Here. So what we're doing now is figure 13 in the draft. So this is also in the draft, I'm sorry, in the physics reports. So you can also follow that and see what happens. And I will come to, there's some subtleties. So we implemented the Borel-Padé. So here's Borel-Padé. So you see that the Borel is really just a sum. And then you see that the Padé is, Mathematica has a built-in Padé approximant function. You can see, well, there's going to be issues here with the resummation. I'll come back to that in a second. But if I deal with those issues, then I can start seeing that I can play the same. And there's 2 plots here that I will discuss next. So the only subtlety that one needs still to take into account is the following. Let me just give you the final subtlety on the iPad. Share iPad. So, oops, it's not connecting. Let's try again. Yes, there we go. So the final subtlety that we need to take into account is that, as you saw in the plot in the Mathematica notebook, when we're doing our Borel-Padé resummation, there were sort of poles. This is sort of saying that it's dirty numerics, but it's there. And then what you have to do is you have to do a Borel-Padé resummation for, it doesn't matter, you just pick one. So here I'm just following what we did. We picked the minus guy, Borel-Padé. And that's the resummation that we do. Now, when we do this, so that's the final subtlety I wanted to mention, is that S minus Borel-Padé n of the 0 to 1 sector actually has 2 components. It's got a real part and an imaginary part. And so you have to be careful, and you could say, what happens with each one of them? Well, it turns out the following, that, and the reason, of course, why it's got the real and imaginary part should be obvious, right? Because we're sort of off the real axis. And what turns out to happen is the following, is that my initial series, the I factor went away because I'm just already looking just at the real and the imaginary part, minus the Stokes guy times the resummation. This should have an arrow on top, I guess. The resummation of the imaginary part of the Borel-Padé of the 0, 1 is of the order 3 to the minus k. So in spite of the fact that there's an imaginary contribution coming along, it won't it will only be relevant on the next step. So in some extent, and it also won't be a problem there, because when you do the next step, it also goes away. And then the real part, which is basically minus S1, the resummation of the real part of the 0, 1. That one is a further, okay, now we already know that there's a real and imaginary part. It's of order 2 to the minus k times S1 squared times F0 to 0 plus so on and so forth. So imaginary part here, no problem. And the real part, what we want. So there are some subtleties, and I'm of course just flashing through the subtleties because it's not really, I mean, this is something you have to really look at the plots and try to play with them to see why they're relevant. I know these not, yeah, we can see them here. So we can go and directly see the plots here, if I can find them. Yes. So you see here, I'm plotting well, this delta is basically just the guy of the real part. This is the shorthand notation. Okay, doesn't matter. So what I need to find here is the Stokes coefficient, and I find it. So here's the initial sequence, and here we find that it's just converging for the number that we want, which was this one. So all that is good. And here, look, I'm putting, that's the imaginary part, and I'm putting 3 to the k. Can you see that? There's 3 to the k. Maybe I can zoom in. Can I zoom in? Sort of. There's a 3 to the k there. And so you see that with 3 to the k, the sequence is order 1. So that's basically telling that it's suppressed to 3 to the minus k, so I really don't care about that. And so we're sort of done with that. And so this allows us to test the second instanton. Let's go back to the iPad. And we see the second instanton appearing. So we can go back to our original sequence. So by now, oops, that's not what I wanted to do. Here, that's what I wanted to do. So we had our initial sequence. We tested the 1 instanton guys. Then we've already seen that we can remove them from there. And we can go on to test the 2 instanton guys. And there's a real and imaginary part. The real part is testing all these guys here. The imaginary part only appears at next order. And then at next order, it won't be relevant. It turns out, I mean, let's not go into the details now. It's not going to be relevant. All right. So having said that, let me just, I think we're almost done. We have like 10 minutes to go. So I'm just going to tell you 2 words. I think I'll probably end a little bit early. 2 words on testing 1 instantons and on telling what else can we do. Okay, I can show a formula of the two instanton as well. So all this game that we've done for the perturbative, then you should iterate. As I said, not necessarily deep in the asymptotics of the perturbative, you're going to find all your non-perturbative content. Some content can only be seen by digging into the asymptotics of higher instanton sectors. So it's important that you don't stop at the perturbative and that you really do a few more tests in order to try to uncover everything that's hidden here in all these non-perturbative sectors. So let me again show you 2 simple formulae. Okay. Asymptotics of 1 instanton. Let me write the formula for the asymptotics of the 1 instanton and then another formula for the asymptotics of the 2 instantons. Because you may recall that, can I find the trend series again? When we finally, by doing this Borel-Padé analysis, we found that the trend series of our toy model was not just what we first initially guessed, sort of quote-unquote standard instantons, but there was another component playing in the game. This told us that beyond the standard Stokes data or Borel data, whatever you want to call it, there was another guy. There was another guy associated to this new sector. And we have not seen any trace of this guy in the perturbative. So that's a sector that by just looking at large order of the perturbative, we wouldn't find. We actually looked at, if you recall, the reason why we realized this guy was there, because we started looking at the Borel-Padés of the 1 instant. The perturbative doesn't see this. So you really need to test the asymptotics of instantons to sort of be able to sort of construct the full trend series that you're looking for. So let me just briefly mention how to do that and how to find these new sectors. So if you write down the asymptotics of 1 instanton, again, let me write a long formula, but that's fine. No, I'll write formulas. I was going to switch to slides, but I think I have 10 minutes, so I think this should be enough to just write down. So here's the 1 instanton now. 1 instanton. And again, I move the factorial and exponential part to the left-hand side. And then what do I have on the right-hand side? I have Stokes data. I have the 2 instanton plus, let me write it just like that, order 1 over k. You already know this, the feeling, and you can always go to the physics report and look at all the formula. And then I get, going backwards, that funny guy. And it's quote unquote exponentially suppressed with -1 because it's 1 step back. I should put an arrow because it's a Stokes coefficient. So I can really see that that other sector is there. And then more exponential, now really exponentially suppressed stuff, 2 to the -k. By the way, here there's nobody else. Remember that this sector was just a constant. So I really just see this. I need to see the resurgence of basically of a number. And here I have the 3 instanton guy. Plus order 1 over k plus order 3 to the minus k. So now you see, okay, this, oh, sorry about that. This part here and this part here, they look exactly like what we've just seen. And so the novelty of the asymptotics of the one instanton is this guy. So what I'm saying is that I sort of have forward resurgence. I see the 2 instanton. I have forward resurgence. I see the 3 instanton. And I have quote unquote sideways resurgence. I see the 0,1. And this appears distinctively in the asymptotics of the one instanton. Let me show you a plot. So again, let me not go through the details of what's how to do the calculation is basically the same that we just discussed. And I want to show you figure 15. Yes, here we go. And so here you can see the asymptotics. And what I'm trying to find here is this S tilde. And so this product should be 1. I mean, it's not very complicated numbers in this simple example, but you can clearly see, so there's sort of an oscillation, a jump back and forth. That's because of that -1 to the k. Here's the, let me not jump to the iPad because the formula is right here. So you have these 2 contributions. They jump back and forth, but that's fine because then they eventually converge to the number you want. And then you see, okay, that one is there. Okay, just bear with me 2 more minutes and I'll shut up. Let me just tell you about the asymptotics of the 2 instantons. Not because I want to torture you towards the asymptotics of 3 instantons, but because they finally show you something nice, which is everybody appears in the game at last somehow. Because with the perturbative asymptotics, which was here, all we had, so we started with the perturbative, all we had was the 1 instanton, the 2 instanton, the 3 instanton, all we had was forward resurgence. With the asymptotics of the 1 instanton, there's a gap here. The asymptotics of the 1 instanton, we had forward resurgence and we had sideways resurgence. And just very schematically, if I do the asymptotics of the 2 instanton, so the same thing of 1 instanton, now 2 instantons. Where's the formula? Here it is. Okay. Let me also just write it schematically. I have the 2 instanton guys. I put exponential and factorial growths to the left. And here I find forward. I find the 3,0 sector plus dot. Then I find sideways. No, I'm sorry. I find backwards. I'm organizing this differently. So here, S-1. I find the 1 instanton sector plus dot. And where's the next page? So you can find it. Plus more forward guys. 1 to the 2k, 6s1 squared. F0, 4,0. Plus, can I fit everybody here just schematically? So you could ask, why am I just putting the sideways at the end? Because of there's exponential suppressions going around. And this is F01 plus, or there's 3 to the minus k. So you can see, let me just, we're looking at the asymptotics. What happened here? This is the wrong, yes. And this is the wrong color. So what I want to do is this. Asymptotics of the 2 instanton. And I see, let me put in green forward. Forward, I see the 3 instanton. Forward, I see the 4 instanton. And the 4 instanton is exponentially suppressed as compared to the 3 instanton. Then I see backwards because I see the guy that came before, which was the 1 instanton. And it's quote unquote exponentially suppressed. It's just a jump back. And there you go. And then I see sideways. Okay, can I fit everybody? I see sideways because I'm finding the sector 0/1. And it's, again, I need to do 2 jumps back with these S tildes, they appear. And so that's sideways resurgence. So it can get really intricate, and you need to test these things. Okay, so let me end by showing you, I think I'll just show you the plot. Again, you can go to the Mathematica notebook and play with it, but for the sake of what we're doing here, let me just share figure 16. There is figure 16. Can I find it? Here we go. And now something funny happens is that it's also oscillating the sequence, just like in the one instanton, there was a -1 to the k that made the sequence oscillate, but it's oscillating between the limit -√2 and 0. And so we see that that's exactly what was supposed to be happening. And we see it happening. All right, so that's about it. So that's another way. So what we've seen basically is 2 ways to try to solve these nonlinear problems. We can start trying to tackle these nonlinear equations that we may have to. And by the way, and sometimes we don't even have equations. All we have is recursion relations like logical strings, or even less in quantum theory. And so there's different ways to try to decode everything that the perturbative series, which is what we usually start having access to, is telling us. And it sometimes gets a little bit dirty. So you have to do some Borel-Padi analysis that we discussed in the first part of the lecture. That tells you about singularities. It starts giving us clues about the residues, the Borel residues of the singularities that also are telling us about Stokes data. Or we can do large order, which is classically what's been done the most. There's a huge literature, by the way. You should look up in the physics report. There's all these references. There's huge literature on this large order asymptotics that was done a lot in the 80s. And that's another way to start tackling these things and try to find Stokes data. And I remember that Stokes data is really the fundamental thing we're looking for. Somehow, if we know Stokes data of a problem, and we have another problem with the same Stokes data that seemingly doesn't look the same, it is the same. So these are actually invariants of the problem that we're looking at. And then there's the more pragmatical question of, if I really want to extend my observables into the complex plane non-perturbatively, I do need to tackle Stokes phenomenon. And this can only be done if I do know Stokes data. I know how to jump from region to region to construct non-perturbatively these new functions. We're sort of, well, not the Bessel function that's been known for 300 years, but when we're trying to solve polyvia problems and we want to tell you what the polyvia transcendent is carefully, we need to tell you about all the Stokes data of polyvia transcendence. That's harder. So that's about it. So I think with the lecture of Friday and the lecture of today, this was the most simple example I could cook up. And I hope that I've illustrated a lot of things that go on in an example that you can just run in a few minutes on your laptop and play a bit with it. And also the analytics, by the way, which is at the end of the day what we're interested in, are sort of very simple because you can always compare against Bessel functions. So what I want to do next time is to sort of formalize these ideas a little bit more mathematically. That would be sort of lecture 3, and start going into the direction why we care about all this, because so far it's been purely formal, and you could say, okay, that's cute, but do I really care about this? And so start telling you, yes. I mean, whenever you're trying to deal with large N theories, string theories, and so on, you basically have to deal with all these things. And then on the final lecture, I'll sort of I will be there in person, hopefully, if my flight doesn't get canceled again. And I will just present lots and lots of results that we've had over the years. I think try to do a review of state of the art. Monica asked me to do a more technical lecture on the final one, so I'll try to do that. So that's it for today. Thank you. If there's questions, please go ahead, shoot.
Yeah, I have a very stupid question. So last time we looked at the partition function, and today we looked at the free energy.
Yeah.
Do we get something more by doing this, or was this just?
This is just, again, I've tried to say this several times. I'm sorry. This is just the simplest possible examples there is. I mean, you know, from a research point of view, these are just completely uninteresting examples. It's just really to motivate pedagogically all the ideas and all these concepts.
So it was just to introduce this nonlinear term.
Just to be as pedagogical as possible, again, in examples that you can work out by hand in 10 minutes and make some, you know, nice plots on your laptop without running for a long time. I mean, in the final lecture, I will show you one thing that we're sort of studying zeros of a partition function in the matrix model, and we want to have an analytic expression for that, of course, but so we needed to have some feeling of the numerics, and that ran for 3 months on a cluster at CERN. So I mean, that's probably not the example I should start off in a lecture. So that's the reason why I've sort of done these two simple examples. Let me also say something else, which is when you're looking at minimal strings and multi-critical theories along the KDV hierarchy, what you're computing most of the time is the specific heat of these problems, and then you still have to make the jump to the free energy and to the partition function. So that was sort of the very vague inspiration of talking about the partition function and the free energy. But, yeah.
Okay, thanks.
Well, no, but look, I mean, again, I think, yeah. No, I was going to say that, I mean, historically, I'm not sure. I was trying to see if Sanchez now was still here, because historically he could help us much more in trying to understand what actually happened. But I think that during the 80s, so I mean, maybe he will listen to this on YouTube and then he can correct me if what I'm saying is right or wrong. I think in the 80s, it's not clear to me how much of this development of ECAL was known to the physicists working on this. Also, André Voris is here. No, he's also not here. So, but either Jean-Jacques or André Voris could tell us more about it. So yet, all these large order tests were done a lot by Jean-Jacques, by the way, without, again, to the best of my knowledge, not knowing a whole lot about resurgence, because these are just simple large order relations that you can come up with by just playing with the Cauchy integral representation. So you don't need to know about this stuff to start playing the game. And computing instantons is something that was known since the 70s, right? And then doing perturbation theory around instanton sectors was also, I think, not very hard. Again, I was not there in the 80s, so I don't know exactly what was going on. The power of resurgence is telling us that, I mean, and a lot of these tests, again, to the best of my knowledge, were done for the asymptotics of the perturbative series. And the power of resurgence is telling you, but you should be actually going beyond perturbation theory, because there's more stuff that that you wouldn't see. And I would say that probably, again, what I'm going to say may be historically wrong, but to the best of my knowledge, the first paper that that actually told us, look, really what you should be doing is looking at the asymptotics of instantons was by Garofalidis, Itzkapev, and Marinho in 2010, looking at the polynomial 1 equation. Where they said, look, there's a surprise here in the two instanton sector. There's more people than what we naively expected. And I think that was probably what sparked what's been going on in the last 10, 15 years. Well, if it was from 2010, the last 12 years. And that's when resurgence really started becoming useful to try to really, put all these on a systematic level, try to really understand how can we go beyond just what we sometimes call canonical Stokes data, which were Stokes coefficients that are sort of easy to compute and that have been computed actually in some of these problems in the 90s already, and start addressing really the hard part, which is all these non-trivial Stokes data. And let's see where it's still bringing us. But it's for sure it's telling us that there's more sectors than what you naively thought at the non-perturbative instanton / deep brain level. Those are being uncovered now.